In the previous video, we looked at the redshift, the blue shift, and how you can use the Doppler effect to see how fast are lights very far away moving away from us and what rate. So this diagram, so our Doppler shift, you see from where we are observing, we are the Earth down there. If you're like super far away, you see that the light coming out from that galaxy or star is a bit red shifted, and those that are nearer to us, okay, you see those are like a little bit green shifted. If that's a term, no, that's not a term. But the speed of recession is not as high. So that is what we looked at in the previous video. So there's this guy, Mr. Hubble, who decided that okay, let's put together this evidence. Let's create this thing called the Hubble's law. So the first fact that he pointed out is okay, observations of distant galaxies, especially those far away, show that for the vast majority of cases, for most of them, the absorption spectra from distant galaxies are found to be redshifted. Most of it. Okay, so except for a few near our Milky Way, of course, but redshift means they're moving away at a certain speed. So this indicates that galaxies are moving away from us. Okay, so he's like, okay, redshift, calculate velocity. Let's do this. Let's plot some graphs. So he created what is called this Hubble diagram, which is a plot of recession velocity against distance for galaxy. Okay, and this recession velocity basically means the speed at which the galaxies are moving away from us. Okay, so you have this graph. Miss Lee, what is this graph about?
Right, so if we look at this Hubble diagram, which is Hubble looking at the distant night sky, and he decided to grab a bunch of stars that he can observe reliably, and then try to plot like an experiment, the recession speed using Doppler redshift versus how far away the star is. So just remember that to arrive to this graph or this data requires the knowledge from the previous subtopic, right? There's the Doppler redshift here. Let me write that down. This is from the Doppler redshift equation. And this distance can be calculated using the luminosity inverse square law. Okay. So we have reliable techniques to measure distances and also the recession velocity of how fast the galaxies are moving away from us. And we notice that the further away the galaxies are, the faster they are moving away from us. So like all good physicists, we got to plot a graph and try to draw a best fit line. And this was Hubble's data. And Hubble later on passed away and passed on his research to future generation of scientists, and they continued his good work. So we went from 0 to 20 megaparsec, which is another unit for distance, to 6,000 megaparsec. So you notice that we are sort of able to roughly draw a straight line, but you probably can tell that there's a lot of scattering, or there's a lot of like data that feels like, like anomalous and doesn't really fit the trend. Okay, so we are now going to try to write down Hubble's law based on the graph and try to explain why there's this scattering of dots, or in other words, why are the dots like not near to the line? Okay, so since this is a straight line graph, let us write that equation down first. Okay, we will use the equation of V. So this is the redshift recession velocity against d, distance of galaxy. So it is approximately equal to a constant times d. And because this is Hubble's law, so the constant that we will use is Hubble's constant. This is your equation. Let me label the value or what each symbol represents for you. So this V here is our recession velocity. H naught here is our Hubble's constant. It's a proportionality constant, so it's a constant of proportionality. And this value of H naught should be given to you, 2.2 times 10 to the power of negative 18 second negative 1. This is experimental data. The best we have so far, right, Miss Ellie?
As of the time where this textbook and the syllabus was written and confirmed and agreed upon by all the scientists. Yes.
Yep. And d here is the distance of the galaxy that is being measured. Okay. So this distance, as mentioned, we use a lot of standard candle methods. So think about your previous subtopic and the recession velocity. Also from the previous videos, this is using the Doppler redshift method, implying that we can obviously include that when trying to see whether you really understand the basic of astrophysics. Okay, so we would like to have a nice straight line graph, and we would like points to be very, very close to each other. But unfortunately, if you have done any physics experiment, you would know that your points are just going to be all over the place. So this is because although the stars or the galaxies are moving away from us, if you look at the video or the GIF in the beginning, you will also notice that some of them are actually spinning. You see this one, the spinning? So when something is spinning, right, sometimes it looks like it is moving towards you, and sometimes it moves like it's spinning away from you because it's spinning this way. So because of all this random motion, the fact that it's also spinning, sometimes you will get different scattering of data. So we'll try to write down the possible sources of error. All right. So the first one, it could be because the galaxies may have rotational motion. And number two, sometimes it's sometimes rotating towards us, sometimes rotating away from us. And then we could also say that the galaxy's recession may be affected by any kind of neighboring things like a big black hole nearby or a big sun nearby with large mass. Okay, maybe influenced by nearby objects with large masses. We don't know. Okay, so these are, yeah.
They could be like moving away, but not in like a linearly away from you. They could wobble around, move curve a little bit due to whatever is influencing them, right?
Mm-hmm. Okay. And also because there's this problem of line of sight. Sometimes we want to observe this galaxy, but then there's another galaxy that passes around. So it affects the data a bit because we are observing this galaxy not for 1 second, it's for like days and days and months and years we're staring at the same star. Right, Miss Ellie?
Yep, always these same stars.
Yeah. The ocean of the galaxies are not always along the line of sight. So this is just in case, you are asked to comment a little bit about the sources of uncertainty and errors. An observer and the source. Source here would be our good old stars. All right. So although Hubble's law is fairly reliable, or this is the best that we have so far to explain what is going on and how every single galaxy is moving away from us, there are a lot of things that we can't really know for sure. For example, the Hubble's constant experimental data is the best that we have so far. Will it change in the future? We do not know. There are a lot of problematic sources of error in the data. This could be because we still have to account for the fact that some galaxies that we don't know could have some rotational motion. And also because there's probably some recession, being affected by nearby objects like black holes. And also there's a problem of not the line of sight. What you're looking at may be blocked by something else. And then you measure the data of that something else. You don't know. So these are just possible guesses. In science, we do a lot of guessing.
Mm-hmm. And science is still growing. There's still a lot we don't know. So for example, this is maybe not in the textbook, but line of sight, when I shine a light at you, I'm assuming the line goes in a straight line to you.
Yeah.
The light. But people have discovered that actually the light itself can also bend if there is some invisible something there that blocks. It's called gravitational lensing, partially. Mm-hmm. But it's like very new research, and we just keep discovering new things. So if this is some field that interests you, astronomy, cosmology, astrophysics, that's where people are still trying to make graphs like these better to understand more about our universe.
Mm-hmm.
Okay, let's go next. So we know this great graph V proportional to D that will be updating over time. What does that tell us? So some conclusions that people came about is this idea of the Big Bang Theory. You may have heard of this before. It's a movie, it's a name thrown around. Not a movie, it's a TV show and a name thrown around a lot. Humans are curious and they're like, well, how did the universe come about? Surely it has a beginning, maybe. Well, from what we see from Hubble's law, we see that galaxies are all receding from Earth and actually from each other, not just from Earth. But we are watching from Earth, so it looks like it's going away from us, all the galaxies and stars, and receding with a recession velocity proportional to distance. That's from Hubble's law, V proportional to D. Okay, so this law, after plotting the graph, shows that the speed of recession is greater for galaxies that are further away. In other words, in English terms, basic English, if you're very far, you're moving away faster. If you're very close, you're moving away slower. Sit down, pause the video, and let that soak in your mind until it makes sense. Like, okay, you can visualize it doing that. Okay, so if you think backwards, say, okay, if they're moving away from everybody's moving away from each other, means this implies that at some point in the past, in a history of time, all galaxies were initially at the same point. Just think like everything's moving away, right? So you rewind, everything come back to each other.
It's rewind time. All of us came from one single dot. You, me, your computer, the cup.
Everything. So that's what people call that's how people got the idea of this theory. No, it's a theory. Nobody was at the beginning of the universe. We don't know. So a Big Bang theory says that the universe begin from a point of infinite density. He also said infinite energy. I mean, infinite density, 1 point, and this is 1 point, so it is called a singularity. And it has been this singularity since the Big Bang, many years ago, has been rapidly expanding lah. So ever since that. Okay, so Miss Lee, what do you think about this Big Bang theory and how does that tell us about the age of the universe?
I think if, let's say you look at the Big Bang theory, right? It's like saying that, well, since everyone is moving away from us, and the further you are away from us, the faster you are moving away. Sounds like a meme, right? The closer you are, the further away you are, the faster you are running away. It means that if I can rewind time, I can actually calculate the age of the universe. I can always assume that when doing this rewind situation, I can look at the speed of light to estimate the age of the universe. So let us write down a few equations that we already know. For example, your brand new Hubble's equation of proportionality. Recession velocity is Hubble's constant times distance traveled. But also we know that the reason why we can observe all this light, assuming there's no bending and gravitational lensing, is that the speed of light is constant. You know that, right? So we also know that I'll write that down. Speed of light, c, is also equal to distance over time. So if you think about the time it took from, let's say, for example, the singular, we don't know where the singularity is, Let's say, for example, in a distant past at a point that we are yet to determine, the Big Bang happened, or the universe expansion happened, and the light from that point in time took a long time to travel to us. Because why? Light takes time to travel at the speed of light. The light wave, the electromagnetic wave, takes its time to reach us, the observer. So when we put this inside, we get distance is equal to speed of light times time, and then I can substitute into the Hubble's equation. But the recession velocity here would be the speed of light, which is c. Okay, and this one will be equal to h0 times d, which will be your ct. Okay, because the fastest possible speed is the speed of light. You cannot run away from the observer faster than the speed of light. So c is the fastest possible speed. Due to Einstein theory of relativity, but This is, scientists agree that your 3 times 10 to the power of 8 is the fastest possible speed that you have. Okay, just going to write this on here. This is your 3 times 10 to the power of 8 meter per second. Well, regardless, your c will cancel off. So we can actually find the value of t, the age of the universe. This will be 1 over h naught. And I know the Hubble's constant. It was 2.2 times 10 to the power of negative 18, experimentally calculated. And if I were to press my calculator, let me adjust the writing a bit, this one would be 4.55 times 10 to the power of 17 seconds. Hang on, I'm missing a unit here. Second negative 1. When you use this equation, right, you have to make sure everything is SI, okay? So this recession velocity have to be in meter per second. And this distance of the distant galaxy will be in meter. Because when it comes to something that is very big, like astronomical scale, sometimes we use different units. But when using the Hubble's constant, please go back to SI. All right, so let's go back to this equation, which is why this one here is in second. Miss Ellie, is this a long time?
I think we need to convert to seconds.
Like our brain cannot.
I cannot deal with this amount of seconds. Maybe let's
10 to
try
the power of 17.
let's try convert it to years, maybe minutes,
Okay.
hours, years. Okay.
Yeah. So
So we need to
let's
divide
convert to
by
years.
say one. Okay, one minute has 60 seconds.
Mm-hmm.
We divide by 60. 1 hour has 60. Wait, 60. 1 day got 24 hours. 1 year got. Depends on how accurate you want to be, but we can go with 365. Okay, let's press calculator.
We're just estimating the age of the universe, roughly.
So if we trust Hubble's law and we say, okay, yeah, there are some flaws, but you just want to estimate, you should get about 40 times 10 to the 9 years. That's a lot of years. That is, what's that, billions?
14 0 0 0 0 0 0 0 0 0.
Billion years,
Oh.
okay.
This here is million.
Million, billion.
Billion. So the whole thing here, billion, no?
Okay, understand.
So in English, not in prefix or physics, we can say it's 14 billion years old. So just, can you even imagine what is 14 billion years?
I cannot, but this is based on, remember, the Big Bang theory and Hubble's law, which is constantly being updated. So it's not like this is the absolute truth, this is the answer for all the questions in the universe. No, this is one theory and one way to approach to find the age of the universe.
We're going to look at some diagrams to help you visualize the fact that there was a singularity and that everything is moving away. So let's say, for example, one of the popular demonstration that we have is like a balloon. You can put different points on the balloon and then you add air into the balloon. So you notice that on the surface of the balloon, all the galaxies, all the bright dots are moving away from each other. So say I look at this distance and this distance, you can see they are just moving further and further away. Everyone is running away from each other, This one is running away.
And it's a bit mysterious because it's not like people is moving away from Earth. It's, you can't find the center of expansion in our 3D universe. It's something that we are missing that we don't really know where. But we know everybody is moving away from everybody somehow.
Yeah, and let's say, for example, if you are here, this is you. Okay, maybe I'll draw an eye here to represent the observer. So wherever you look at, everyone is running away from you. Just like if, let's say, there's another alien species also looking into the night sky, who knows? Maybe there's another alien here with purple eyes, and everything is also moving away from this alien. You can see the distance are just getting longer and longer. Okay, so when you think about the singularity, right, or the fact that when we are estimating the age of the universe, if we were to rewind time a bit, so let me show you this demonstration. If we look back in time, all of this started at a point. And if I can pause a GIF, which I unfortunately can't, currently, right, we are, okay, let me screenshot this and throw this inside. So this is our current state of the universe, and we can't tell where it started from, right? I mean, you can tell because there's an animation, and then, we go back in time, and then we rewind time, but we are not God, so we can't rewind time. So you don't really know where it started from. If I just randomly take a screenshot, we are currently at a corner of the universe. Let's say this is you tiny little human here. And you're looking around, and you can only see maybe this section of the universe, and then you see all the stars are running away from you. And let's say the center, the universe started from here. Let's say only I don't know where. Let's say it's here. See. So by the time the light travels to your eyes, we actually use Hubble's law to determine the time taken t. That was what we were doing just now. Okay? So that time taken for the light to travel to your eyes is limited by how fast the light can travel. So this is Big Bang Theory. We started... What was the song again from Big Bang Theory? Whoops, my OneNote is glitching. Hang on a sec.
There's a song for Big Bang Theory?
Yeah, the Big Bang Theory intro song from the comic.
Go and search in YouTube.
The whole universe was a hot, dense space. And then as time passes, space began to expand. So if let's say we plot
still expanding.
Yeah. Are we still expanding, Miss Ellie?
Yes, I mean, according to theories, this is all a lot of just theories. So if you're interested to know more, and don't worry, they won't ask you on the test like, oh, how is the universe going to end? They will ask you to suggest based on what observations you see, what can you infer when you trace backwards in time. But all this is still updating. There's still a lot we don't know for sure. There are a lot of theories, a lot of pictures. You can definitely go and Google them out.
So I think we will end today's video with this.
So as we wrap up this whole A2 physics, AS A2, we end with this. So your homework next to think about for the rest of your life maybe is to think, ask the question, how did the universe begin and how will it end? Our lifetime we won't see that. All we can do is just guess, or if you're down for it, actual research, go for it. But if not, you can think about your existence. Why am I here? What's going on? What universe?
You can add another dot on Hubble's diagram.
Okay, so I think that's all for the video and also the whole syllabus of A2 for now at the time of recording. All the best for your exams. See you in the examples videos. Oh yes.
Bye-bye.
All the best in the universe. See you somewhere in the universe someday, maybe. Bye-bye.